Welcome back. We're having our second invited speaker, François Le Gall, who's been at every ACUS and ECUS since
almost.
Yeah, it was a since 2003. So he missed the first two, but that's pretty good, nevertheless. So he's at the University of Tokyo on faculty, and he will talk to us about matrix multiplication.
Thank you. Okay, so the subject of this talk will be quantum algorithms for matrix multiplication. And so this talk will... I think so, yes, but... This talk... Okay, so this talk will consist of 3 parts. In the first part, I will give an overview of the complexity of a matrix multiplication. So focusing on the 2 most basic kinds of matrix multiplication, the usual matrix multiplication, so over a field, and Boolean matrix multiplication. And I will also show how, in some circumstances, simple quantum algorithms can outperform classical algorithms for these 2 kinds of matrix multiplication. Then I will move to a second topic, which has been the subject of instance study recently, which is the construction of fast quantum algorithm for sparse Boolean matrix multiplication. So when the input matrices or the output matrices are sparse. And in the last part, I will describe a recent work I obtained with Harumichi Nishimura from Nagoya University about fast quantum algorithm for other kinds of matrix multiplication connected to many graph theoretic problems, such as the distance product or the max-min product. So first, this overview of the complexity of matrix multiplication. So the problem we are considering is the following. So we have two matrices, two square matrices of size n by n, so A and B, with entries in the field. So for example, real entries, or even in a ring, so integer entries. And we want to output the product of A and B. Okay, so the standard product of A and B. And of course, this is one of the most fundamental problems in mathematics and computer science, and matrix multiplication has a multitude of applications, so to cite only a few of them, so many linear algebra problems. For example, the complexity of computing the determinant is known to be equivalent to the complexity of multiplying 2 matrices. Polynomial factoring, so the best known deterministic algorithm to factorize a polynomial use matrix multiplication. So also matrix multiplication, a lot of applications to graph theoretic problems, and there are also applications to computational geometry and even to computational complexity. So for instance, the celebrated recent result by Ryan Williams on circuit lower bound used the complexity of matrix multiplication. Okay, so it's a very fundamental problem. So what is the straightforward algorithm to compute the matrix product? So it's the algorithm we learned in high school. So it's follows from the definition of matrix multiplication. So Cij, so the entry in the ith row and the jth column of the output matrix is defined as follows. So if you want to compute this directly, this will require n multiplications and n-1 additions for each entry of the output matrix. And since there are n square entries, we obtain this complexity, so cubic complexity. This is the simplest thing. So the algorithm we learned in high school following from the definition of matrix multiplication. But actually, we can do much better. So classically, the best known algorithm has complexity n to the 2.3727. Okay? And as I said, so matrix multiplication is one of the most fundamental problems. So computer scientists have studied this problem for a long time, and they have even designed a notation for the exponent in the complexity of matrix multiplication. It's usually called omega. Omega represents the exponent of square matrix multiplication. So technically, this is the infinium of all the tau, such that the product of two n by n matrices over a field can be computed in big O n2 arithmetic operation. So informally, this means that omega is a minimum value such that the product of two n by n matrices can be computed with big O n omega arithmetic operation. So technically, it's maybe the limit of a family of algorithms, so that's why we need an infinium here and not a minimum. Okay? And so this means that the straightforward algorithm shows that omega is smaller than 3. And this algorithm shows that omega is smaller than 2.3727. Okay? But it took a lot of time in order to achieve this bound. And here in this slide, I show the history, rough history of improvements on the giving upper bound on omega. So, of course, we have this trivial upper bound. And the first who improved over this trivial upper bound was Strassen in 1969. Okay? He obtained upper bound 2.81. And then there have been a few improvements. And then in 1981, Schonhager obtained a very new technique, proposed a very new technique, and was able to obtain the upper bound 2.55. And then there was, with the same technique, a few improvements. And at that point, many researchers believe that, well, this should converge at 2.5. This is natural. Yeah, well, but no, actually, you can do better than this. Okay? And then again, Strassen struck back and obtained this. And then Coppersmith-Winograd obtained this very famous upper bound, 2.376, which was unbeaten for more than 20 years. And recently, Stothers and Vasilevska-Williams obtained a slight improvement of this. So the current best upper bound on omega is this thing. And of course, we can ask, what is omega? To what value this thing converge? And it's widely believed that omega is equal to 2. Okay? Omega should be larger than 2, because you need to output a matrix of size n squared. So we need at least one arithmetic operation per entry. So you need at least n squared arithmetic operation. And it's believed that this is tight. So omega is equal to 2. But it's only a conjecture. We don't know how to prove it. Okay, so I would like to spend a few minutes explaining the rough idea behind this algorithm by Strassen. Okay, the first algorithm beating as the straightforward cubic time algorithm. So it's a classical algorithm. So the bound obtained is n to the 2.81. And the idea is very simple. So you consider the multiplication of 2 by 2 matrices. So A and B are 2 by 2 matrices. So for 4 entries. And the product, of course, is a 2 by 2 matrices, so 4 entries. And if you want to compute this using the straightforward computation, you will need 8 multiplications. Okay? 2, yes. So 2 multiplications per entry. There are 4 entries, so 8 multiplications and 4 additions. And Strassen observed that actually you can do it with 7 multiplications. Okay. You can compute the 4 entries of the output matrix by summing some terms, so with some additions, but summing only 7 terms, each term being obtained by taking 1 multiplication. So you can do it with only 7 multiplications. Well, we need 18 additions. But if you look only at the number of multiplication, you reduce it from 8 to 7. And then we can iterate this. So if the matrices A and B are of size 2 to the k by 2 to the k, you decompose this into some matrices of size 2 to the k minus 1 by 2 to the k minus 1. And you can use the same technique. You can compute this matrix product with 7 multiplication of 2 matrices of size 2 to the k minus 1 and 2 to the k minus 1. And you iterate this, and it's easy to see that after doing the iteration, you will need only 7 to the k scalar multiplication to compute the product of the original 2 matrices. Okay? And 7 to the k is the size of the input matrices to a log 2 to 7, which is 2.8073, so that's why we obtain this. Okay? Of course, there are many additions, but it's easy to show that the complexity is dominated by the number of multiplications. So you don't need to take in consideration the number of additions here. But the important thing here is that this scheme works because we are working on a ring. So we are allowed to do negation, to perform the negation on entries. Okay? So we are working on a structure, an algebraic structure, on which there is a negation, a ring. And this will be fundamental because later we will consider a Boolean matrix multiplication and distance matrix multiplication, which are multiplication defined on a structure where there is no negation. So for all these things, we won't be able to use all these techniques. Okay? So the key idea is, again, you take some linear combination of the entries and you perform multiplication and you combine them in order to obtain what you want. And all these algorithms use the same idea, taking combination, linear combination, multiplication, and then regrouping everything. And those, they are called algebraic algorithms. But I should stress that, except the first one, all these other algorithms are not efficient. Well, theoretically they are efficient, but they are only of a theoretical interest. Why? Because the exponent is this, but there is a constant hidden in the big O notation. And the constants are huge. Very, very huge, 1,000, 1 million, or something like that. So in order, for example, to obtain an improvement, over the straightforward algorithm by using this, you will need matrices of size 1 million, 1 by million, or something like that. And for this kind of matrices, you can expect that they will have a lot of sparsity or some structure, and so you should be able to use other things. So this is only for theoretical interest. But I should say that we don't know any better quantum algorithm for this problem. Okay, so multiplying two matrices over a field, the best known, well, we don't know any quantum algorithm, so the best known is to use, the best thing that you can do is to use a classical algorithm with this complexity. There is still a slightly different setting where you can obtain some speed up by using a quantum computer. So in 2009, Arrow, Asidim, and Lloyd have shown that if you are not interested in computing explicitly the output matrix, so all the n-square entries of the output matrix, but instead it's enough for you to compute a superposition, a quantum superposition of all the entries, then you can solve the problem in polylog n time, so exponentially faster than the best classical algorithm. But, well, there is a technical condition that the matrices A and B should be well conditioned, which means essentially that the distance between the eigenvalues, the distance between any two distinct eigenvalues of the two matrices should be quite large, okay? Non-negligible, because it's only a technical condition. But in this talk, and for many applications, we really want to compute explicitly all the output, all the entries, all the n-square entries of the output matrix. So we cannot use these kind of things. And again, in that setting, we don't know anything better in the quantum setting. So the complexity is still n to the 2.3727 using classical algorithms. Okay, now I will discuss a different kind of matrix multiplication, the Boolean matrix multiplication, for which quantum algorithm can outperform classical algorithms. Okay? So Boolean matrix multiplication considers a case where the two matrices A and B are Boolean. Boolean simply means that the entries are 0 or 1. Okay? And the output should be what we call the Boolean matrix product of A and B. So the Boolean matrix product of A and B is very similar to the usual matrix product, but the addition is replaced by a logical OR. And the multiplication is replaced by a logical AND. Okay, so the entry Cij can be generically written in this form. And on this example, for example, so the Boolean matrix multiplication of this and this is equal to this. So especially here, you obtain 1 and 1, which is equal to 1, or 1 and 1, which is equal to 1. Okay, so it's not 2, it's not 0. So we are not considering integer matrix multiplication. We are not considering multiplication of binary matrices over a binary field. We are considering Boolean matrix multiplication. So this is the point. And Boolean matrix multiplication is a fundamental problem in computer science as well, and has a lot of application, mostly related to graph theory. So for example, computing the transitive closure of a graph, or detecting if a graph contains some structure, or solving many network flows problem reduce to computing the Boolean product of two matrices. So the idea to understand this connection between Boolean matrix multiplication and graph algorithm is the concept of adjacency matrix of a graph. Okay, so here we have a simple graph. We consider the adjacency matrix. So this means the adjacency matrix is defined as follows. So we have aij equal to 1 if and only if there is an edge between a vertex I and vertex j. So for example, here between 1 and 2 there is an edge. So you have a 1 here, and between 1 and 4 there is no edge, so we have 0 here. Okay? And if you compute the Boolean matrix product of A by itself, you obtain this thing. And you can see that you have a 1 at entry I and j of the product A2, if and only if there is a path of length 2 between vertex I and j. Why? Because from the definition, the value is 1 if and only if there is a k satisfying this condition. So there is a path from I to k and a path from k to j. So a path of length 2 between I and j. Okay? So you see here the connection between Boolean matrix multiplication and computing connectivity properties of graph. That's why it's one of the most important problems in computer science, the computation of Boolean matrix multiplication. So the trivial algorithm for computing the Boolean matrix multiplication, of course, n cube, classically, for all output, all entries of the output matrix, you check if there exists a k satisfying these conditions. So this require n cube arithmetic operation, n cube operation, sorry. But the best known algorithm has complexity n to the omega. Okay? Because we can reduce Boolean matrix multiplication to integer matrix multiplication. It's very simple. So you have your two Boolean matrices. You consider your two matrices as integer matrices. You compute the integer matrix product. And then you convert all the non-zero entries to 1. So 2 will be converted to 1. And then you obtain the Boolean matrix product. Okay, the result of the Boolean matrix product. Okay? So the best complexity is this. And we don't know how to do better. The problem looks easier, but the best upper bound that we have is the same as computing the product of two matrices over a field or a ring. So now, quantum algorithm for Boolean matrix multiplication. So the trivial quantum algorithm is quantum search, using quantum search. Okay? So suppose that you want to compute one entry, Cij. By definition, Cij is equal to 1 if and only if there exists an index k satisfying this condition. And of course, you can search k using quantum search, Grover algorithm. Grover algorithm shows you how to find a solution among large n elements in square root n time. And here we have large n is equal to n. So complexity will be square root n. Okay? So here we are using the notation tilde. It's a usual notation in computer science. This means that we are neglecting all polylog factors. Okay? We are considering only the value in the exponent of n here. That's the best non-classical algorithm. But then we can consider rectangular Boolean matrix multiplication. It's the same, but the matrices are rectangular. So the first one is of size n by m, and the second one is of size m by n. So the size of the product is n squared, okay, n square entries. And again, you can, if you use the quantum search for computing one entry, you know you need to search for an index k in a set of integer from 1 to m, so the complexity will be square with m. And if you want to compute all the n square entries, the complexity will be this. But now, suppose that m is equal to n squared, so for example, then the complexity here will become n to the 3.5. And it is known that the best known classical algorithm for this problem has complexity n to the 4.2073. Okay? So we obtain a gap here. And even we can actually show that any classical algorithm for this problem require n for time. Why? Well, it's not a strong bound. It's simply that the input matrix has size n by n cube. So n to the 4 entries. So any classical algorithm will need to read out all these entries. So you will need this complexity. So you obtain this gap. So we are in a situation where quantum computation perform better than classical computation.
But here you qualify you need algebraic classical algorithm.
Yeah.
That's a restriction.
Yes, actually, yeah. So the proof, yes. More formally, what we can say is that any classical algorithm for this problem that also works for a multiplication over the ring will need this complexity. Okay, so it's a formal statement. You're right. There is this restriction of the kind of algorithm we are considering here. Okay, so summary of this part. So classically, for square matrix multiplication of a ring of field, the complexity is n to the omega. This is the best bound known on omega. For a Boolean matrix multiplication, it's the same. For rectangular matrix multiplication, we have a non-trivial bound. So even for a ring or for Boolean matrix multiplication. And in the quantum setting, we don't have any improvement in the three. We don't know any improvement in the three categories here. But we know that when we are considering rectangular Boolean matrix multiplication and m is large, then we can obtain a gap. Okay? So it's among the four settings here, this one is the only one where we know that there is a gap between classical and quantum computation. Okay? And I believe that the most fundamental open problem in this field is really to improve these two bounds. So consider the most natural setting. So we have a square matrix multiplication over a field, a ring, or Boolean matrix multiplication. And we really want to know whether quantum computation can help, whether we can obtain better bound using a quantum computer. Okay, so this is really the main open problem in the field, I think. And I would like to mention a few results which are a little bit different, but very related, which are not the computation of the matrix product, but the verification of matrix product. So in this problem, so we have three matrices, A, B, and C, and we want to check if C is equal to A. So we are given C, a candidate for the product, and you want simply to check if the candidate is correct or not. So it's a problem which is easier. And classically, so over a field or a ring, the complexity is n squared. It's very easy to construct an algorithm, a randomized algorithm for this problem. But for Boolean matrices, we don't know how to do better than the complexity for computing the product. But in the quantum complexity setting, you obtain improvement with respect to this. So over a ring, or field, we obtain complexity 5 over 3, exponent 5 over 3. And for matrix multiplication of Boolean matrix, for Boolean matrix multiplication verification, we obtain complexity n to the 1.5, exponent 1.5. And it's trivial. Simply, you are doing a trivial quantum search. You are searching for 1 and 3, such that this one and this one will differ, on which this one and this one will differ. Okay? So it's a very easy, simply a quantum search, complexity giving exponent 1.5. Okay? So in this setting, for verification, we obtain a gap. We know a gap. But for matrix multiplication, we don't know any gap except in the fourth setting. Okay? So now I will move to the second part of this talk. So as I mentioned, the main goal is to consider to improve these two bounds for square matrix multiplication. And among these two, this one, Boolean matrix multiplication, seems easier for quantum computation for two reasons. First, for rectangular matrix multiplication, indeed, we obtain an improvement in the Boolean case. And even for matrix product verification, we obtain a better improvement here for Boolean matrices. Okay, so quantum algorithm seems to be to perform better for Boolean matrix multiplication than for matrix multiplication over a field or a ring. So we'll focus on this one. Okay, and we still don't know how to do it better on the quantum computer, but I will show that. If you suppose that the input matrices or the output matrices are sparse, so contain few non-zero matrices, then we can construct quantum algorithms which are much faster than the best non-classical algorithm. Okay, so this is the first step into proving that you can do something better for square Boolean matrix multiplication using a quantum computer. Okay, so let's look back at the algorithm, the trivial algorithm for Boolean matrix multiplication I mentioned a few minutes ago. So for computing one entry, you do a quantum search finding the k, so the complexity square root n. Okay? So we are considering square matrices here. And for computing all the entries, complexity n to the 2.5. Okay? So it's exactly the same as what I mentioned a few minutes ago. But now, suppose that your output matrix C has only L non-zero entries. So L is a parameter between 1 and n squared. Then I will show that we can do it with this complexity. The idea is as follows. So you will do successive quantum search, searching for all the index ij satisfying this condition. And quantum computation, the quantum algorithm will select for you all the ij satisfying this condition. So more precisely, so let's consider the first entry. So you do first a search over the space of index ij. There are n square possibilities. And we know that there are L solutions. So we can use the version of quantum search by Grover for multiple solutions. Okay? So find one solution among large n elements is this complexity where m is the number of solutions. Here we have large n equal to n squared. And the number of solutions is L. So we obtain this complexity for the search on ik. But we need to check whether Cij is equal to 1 or not. And for this, we use this part. So another search on the space of k here. So this gives you a factor square root n for checking if Cij is equal to 1 or not. So we obtain this complexity to find the first entry of the first non-zero entry of your output matrix. And then you do the same to find a second non-zero entry. It's the same, but now we have one solution less. So we have only L minus 1 solutions. And we'll continue this. And at the end, for finding the last entry, you will have only one solution. So the cost will increase to this. And if you solve this, if you compute this, it's very easy to show that what you obtain is essentially L times the complexity of the first term. So you obtain this, n to the 1.5 multiplied by square root L. Okay? And this was first observed by Bellman and Spalek in their paper on verifying matrix products. So it will be very convenient to write this complexity on a graph. Okay? So a vertical axis of the graph will represent the log of L. So L is the number of non-zero entries in the product. A log with respect to basis n. And the vertical axis will represent the log of the complexity, again in basis n. Okay? So these bounds correspond to this line. Why? Because for L equal 1, that is for log L equals 0, you obtain complexity n to the 1.5, so this point. And for L equal n squared, so for the log equal 2, we obtain this point. Okay, so complexity exponent 2.5, so complexity n to the 2.5. So we obtain this straight line. So what is this parameter L? The parameter L represents the sparsity of the output matrix, so the number of non-zero entries in the output matrix. And such algorithms where the complexity depend explicitly of the number of non-zero entries of the output matrix are usually called output-sensitive algorithms for Boolean matrix multiplication. And they have been studied also intensively in the classical setting. And the best known upper bound for this problem in the classical setting are depicted here in blue. Okay? So when L is small, you have complexity n squared. You will still need n squared because you need to read out the input matrices. And when L is log L is very close to 2, you obtain very dense output matrix. You obtain the exponent omega. Okay, so 2.373 2.3727 for the best known bound. And the function between the two is a piece linear. Okay? And you see that this the algorithm by Berman and Spadek is better than the classical algorithm when log L is smaller than 1.602. Okay? But actually, we can do much better than this. So in 2012, I showed that you can obtain the complexity depicted in purple here. Okay, so when L is small, so when log L is smaller than 2/3, you obtain complexity n to the 1.5, and then it goes up linearly up to 2.5, exponent 2.5. And a few months later, Jeffery, Kothari, and Magnez improved this bound in the query complexity setting. I will explain what is the query complexity setting in the next slide. And they obtain this bound, okay, this straight line. So complexity n square root L, number of queries. So it's query complexity. And they have shown that this query complexity is optimal. So you cannot do better than this. And the proof of optimality is actually quite easy. But this follows from a simple reduction from a problem called L threshold. So L threshold is a problem asking to detect if a binary string given as an oracle has exactly L non-zero entries or not. And we know this lower bound for this problem, S threshold. So that's why they obtain directly the lower bound for this problem. So this is optimal. You cannot do better than this in the query complexity setting. And so what is the query complexity setting? So in the query complexity setting, we are considering only the number of accesses to the entry of A and B. Okay, so we are not considering the pre-processing times, the post-processing times, and all the other things. We are considering only as the number of accesses to the entries of A and B the algorithm uses. So the query complexity is always smaller than the time complexity, and in particular, the query complexity is always smaller than 2n squared, because with 2n squared, you can read out completely A and B. Okay? And we can ask, of course, whether we can improve this in the time complexity. And the answer is yes. Well, in the time complexity, what we can obtain is a red line here. Okay? So in formula, here is the first zone, you have complexity n square root L, and then you have complexity L square root n. So even in the time complexity, in this region, you obtain the same bound. And of course, in this region, this is optimal, because you have an optimality result for the query complexity setting. So you cannot do, the query complexity is a lower bound on the time complexity. So you have the optimality immediately. So what about this bound? Can we show that it is optimal? Well, actually, unfortunately, we don't know any interesting technique to prove lower bounds on time complexity for this kind of problems. But, well, we can show some indications that at least we will need completely new techniques in order to improve this. So we can show that any improvement using the same techniques would lead to a quantum algorithm based on search with complexity with exponent 2.5 minus epsilon for L very close to n squared. So what does it mean? So suppose that you can improve, say, this point using the same technique, so you can lower the time complexity here. So then we can show that this improvement will also give an improvement in this zone. So for L close to n squared. Okay? And if the improvement is used using the same technique, so using search, the improvement here will be also an algorithm, quantum algorithm based on quantum search. So we would have a quantum algorithm based on quantum search beating the 2.5 barrier for completely dense output matrix. And this would be a breakthrough, because it would mean that using only quantum search, you will be able to find one entry of AB with amortized cost strictly less than square root n. Okay, so this is not a proof of optimality, of course, but that shows that in order to improve this, you will really need techniques, completely different techniques. And now I would like to explain briefly how we obtain all these bounds, so in particular how we obtain this bound. So there's a bound in green. So these bounds are obtained by using a reduction from matrix multiplication, so Boolean matrix multiplication, to a graph theoretical problem called graph collision. Okay, so this reduction was first observed by Vasilevska-Williams and Williams in 2010, the classical complexity paper. So remember, what we want to solve is this problem, so matrix multiplication. We want to find all the ij, so in this space, satisfying this condition, so all the non-zero entries, and these things, remember, means that there exists a k satisfying this condition. And in order to reduce this to a graph theoretic problem, we will introduce the following graph. So it's a tripartite graph. Okay, so we have three sets of vertices, of n vertices here, n vertices here, and n vertices here. And then we will make this bipartite graph complete. So we will connect any two pairs of vertices. Okay? And then we will connect I vertex with a k vertex if and only if aik is equal to 1. Okay? So for example, here you have a21 is equal to 1, so we connect this vertex, this 2, to this vertex 1. And here we have a and n equal 1, so we connect this thing and this thing. And similarly, we'll connect a j vertex with a k vertex if and only if bkj is equal to 1. So here we have, if you have b and k equal to 1, we connect this one to this one, and so on. And now it's easy to see that to compute the matrix multiplication, the Boolean matrix multiplication of A and B, it's sufficient to find all the graph collisions of this graph. So this means to find all the edges ij involved in the triangle. So let's see why. So for instance, here you have a triangle. Okay? You have a triangle here, which means that A21 is equal to 1 and BIN is equal to 1. This means precisely that C2n is equal to 1 from this definition. Okay, so the definition of C21 is equal to 1 means precisely this thing equal to 1, this thing equal to 1. So once you find one triangle, you find one non-zero entry of the matrix. Okay? And then you can delete this edge and try to find another triangle. And if you find this triangle, then you will know, for example, that Cn1 is equal to 1. So you obtain another non-zero entry of the output matrix. And you can repeat this process. And if you're able to list all the edges ij involved in the triangle, then you obtain precisely all the non-zero entries of the output matrix. So you simply need to solve this graph theoretic problem. Okay? So how can we do this? So initially, remember, this graph is a complete bipartite graph. Okay? And we want to find one edge here, for example, this one, involved in a triangle. And we are claiming that, so for finding the first collision, this is this point, we are claiming that we can do it in a linear complex, with linear complexity. And actually, yes, there is a very simple algorithm for doing this, proposed by Jeffrey Kottari and Maniez. It's simple, but very insightful. The idea is to do the search first on k. So you will search for, find a k for which there exists ij satisfying this condition. Okay? And if you find such k ij, this will give you one edge involved in the triangle. So they will give you the first collision. So what's the complexity of this? So we are doing quantum search over k. This is n possibilities. So the complexity is square root n, no problem. And then we are doing a search on this space. So it's a space of size n squared. But the point is that there is no correlation between I and j. The set here is a Cartesian product. And here, there is no correlation in the two conditions. So you can first try to find a I in this set satisfying this condition, and then try to find a j in this set satisfying this condition. So the complexity is not the square root of n squared, it is square root of n plus the square root of n. Okay? For finding the first collision. So the complexity becomes n. It's very simple. Find search k, then search I and search j. So the search on I and j is independent. So you have square root n plus square root. And then you will remove this h. So after that, this part will not be a complete bipartite graph anymore. And this means that the space here will not be a Cartesian product anymore, but this will be this set where you remove all the edges, all the collisions found so far. And then you will have a correlation between I and j, and you won't be able to use the simple trick we used in the previous slide. And you will have to do something much more involved. And Jeffrey Kothari-Manias have shown that even in this setting, so we obtain the complexity n plus square root m. Okay? So when m is small, you obtain essentially the same thing as in the previous slide, a big O of n. And using these bounds, they directly obtain this straight line. And the time complexity upper bound is obtained similarly. So essentially, we show time-efficient implementation of this algorithm. Okay? This involved a lot of work with data structure, because in the query complexity, we don't need to consider how we store, what we receive, and so on. But in the time complexity, it's really crucial. So we have a lot of additional work about manipulating and storing everything in data structure. But we show that when m is small, we obtain the same bound. And so we obtain this. But when m is not small, then the complexity increases a little bit. That's why we don't obtain the same complexity in this region. Okay? So the conclusion of this part is that so we obtain in the time complexity setting the complexity depicted in red, which means that when L, the number of non-zero entries in the output matrix is smaller than 1.7 n to the 1.779, so smaller than this value, then this red complexity is smaller than the blue complexity represented the best non-classical algorithm. So quantum algorithm perform better than the best non-classical algorithm. So it's another setting when quantum computation wins. And of course, we can ask if we can obtain similar results for sparse input matrices. Because in many applications, we don't have directly a sparsity condition on the output matrix, but rather you have a sparsity condition on the input matrix. And the answer is yes. So we have shown that, so if you consider two matrices A, B with at most m non-zero entries, so m will be smaller than n squared, so m represents the sparsity of the matrix, then you can construct a quantum algorithm computing the Boolean matrix product of A and B with this complexity. So let's put this in a graph. This corresponds to the complexity depicted in red. Okay, this complexity. So when m is small, we obtain complexity n squared. Typically because we need to read out all the entries in the input matrix. And when m is large, we obtain the well-known value omega, okay, the exponent. But between the two, we obtain a straight line here. And this is better than the best non-classical algorithm. The best non-classical algorithm has a complexity depicted in red here. Sorry, depicted in black here. Okay? So, for example, when m is this value, what you obtain is quantumly 2.2754, and here complexity 2.3727, so this point. So you obtain a gap of typically n to a gap of 0.1 in the exponent. Okay. So for in this region, for moderately sparse input matrix, you obtain an improvement by using quantum computation. Okay. And I will give very quickly an overview of the algorithm. So we have two input matrices, A and B, and we suppose that they are sparse, so they have only m non-zero entries. So what we do is the following. We first select the dense rows of P, okay? Where dense means that there are at least r non-zero entries in the row. R will be a parameter depending on m. Okay, so there are many non-zero entries, the meaning of the word dense. So for example, here, let's suppose that the dense rows are 1, 4, and 8. Then we select the corresponding columns of A. So the columns with the same label, 1, 4, and 8. And then it's easy to see that the matrix product of A and B is equal to the sum of two matrix products. The first one obtained by taking the matrix corresponding to the blue columns of A, and this matrix corresponding to the green rows of B. And the second product involves the other columns of A and the other rows of B. Okay. And the point is that if M is small, so if the input matrices are sparse, then we expect to have a few dense rows. So there will be only few rows here. So this matrix multiplication will actually involve rectangular matrices. And if the matrices are rectangular, we expect that we can do the computation much faster than this bound. This bound is for a square matrix multiplication. Okay? And in the right part, we selected the other rows of B. Other rows, that means the rows which are not dense, so rows which are sparse. Okay? And if we know that the rows are sparse, we know that there will be few non-zero entries in this matrix, and then we can simply compute this Boolean matrix multiplication using a straightforward algorithm, basically an exhaustive search. And we can use quantum search techniques there. The application, again, is not completely trivial because you have to take care about the data structure, you have to keep in memory all the information you get and so on, so there is some further work. But the idea is that we can break this into two parts. The left part is handled using classical rectangular matrix multiplication, the right part using quantum search. Okay? Okay? And so the complexity will be the sum of the complexity for computing this and the complexity for computing this. And all the subtleties to choosing the parameter R. If you choose R too small, there will be many dense rows. So this thing will be mainly almost a square matrix, and we don't obtain any speed up by using rectangular matrix multiplication. If on the other hand you take R too large, then this matrix will be very dense. So we don't obtain any improvement by using quantum search here. Okay, so there is a trade-off in the choice of the parameter R. Okay. And if you choose R carefully as a function of M, so the number of non-zero entries in the input, what you obtain this bound, okay, the red line. Okay. So in particular, we obtain a quantum algorithm better than the best non-classical algorithm in the time complexity setting in this region. So for when M is, when the sparsity of the input matrix is between these two values. So for reasonably sparse input matrices. So this is another setting of a sparse Boolean matrix multiplication where quantum computation performs better than any classical, than the best known classical algorithm. So now I will move to the last part of it. So up to this point, we have shown a quantum algorithm faster than the best known classical algorithm for sparse square Boolean matrix multiplication, but for sparse multiplication. And really what we want to solve is the main open problem as this case and this case, so dense square matrix multiplication. So can we find a setting where you can obtain a speed up by using quantum computation even for the multiplication of dense square matrices? Again, we don't know how to do it over a ring or for Boolean matrices. But then we can try to consider other kinds of matrix products. And this is what I will do in this part. So matrix multiplication is defined as this. So it's a definition we learned in high school. And the point is that in order to define this, we only need an addition and a multiplication. Okay? We only need an addition and a multiplication. So we don't need any, all the axiom of a ring or a field or anything like that. So you only need an addition and multiplication. In particular, we do not need a negative inverse or subtraction. Okay? So technically, we can define matrix multiplication over any what we call semiring. Semiring is like a ring, but you don't have any, you don't have a negative inverse for each element. Okay? So we can define matrix multiplication for very general algebraic structures. For example, Boolean matrix multiplication. It's an example of a matrix multiplication over a semiring. So technically, what we call the Boolean semiring. So the addition is a logical OR, the multiplication is a logical AND, and the point is that there is no additive inverse. So for example, if you look at the element 1, and you are asking for the negative inverse of 1, so the negative inverse of 1 should be an integer a, sorry, value a, such that 1 or a is equal to 0. And of course, there is no solution to this equation. Okay? A has only two possibilities, 0 or 1. And for both possibilities, this gives you 1 here and not 0. So this set, called the Boolean semiring, does not have an additive inverse. Okay? So it's one of the examples, most canonical, most simple examples. But there are also many different kind of matrix products defined over semirings, and probably the most useful matrix products defined over this kind of semirings are called the distance product and the max-min product. So they are defined as follows. I will give an example in the next few slides. So the point is that the multiplication is a max here, and the addition represents a min here. So it's not multiplication. Addition is max and min instead. And here, the multiplication is a max. Sorry, the addition is a min here. So the first one is the addition, so the min. And the multiplication is a plus. It's a little bit tricky. The multiplication is the usual plus here. So we obtain this definition. So we can define these two matrix products. And these two matrix products are a lot of applications for graph algorithms. And I will give more examples in the next two slides. So let's start with the distance product. So defined, as I mentioned, in this way. So in this slide, I will give an illustration of the definition and also an illustration of the application of this. So let's consider the adjacency matrix of the directed weighted graph. So here we have a directed weighted graph. Okay, so it's a graph. Each edge has a weight. The weight can be anything, any real number. So for example, we allow here also rational numbers. And we suppose that when there is no edge, we assign weight infinity, plus infinity. So we obtain this adjacency matrix with this convention. And if you take the distance product of A by itself, you obtain this matrix. Using this definition, you obtain this. So for instance, if you look at this entry, 2.5, the entry 1, 4, the first row and the fourth column. So from the definition, the mean of these four terms. Okay, A11 plus A14, A12 plus A24, A13 and A34, and A14 and A44. And if you compute it, it's infinity plus infinity, 5 plus 1, 2 plus 0.5, and infinity plus infinity. Okay, so the minimum is this one, 2.5. And what's the meaning of this? What is the graph theoretical interpretation of this? So each of the four terms represents the length of a path of two edges from 1 to 4. So for example, this one represents the length of the path 1, 3, 4. So this one, 1, 3, 4. Okay? And this one represents the length of the path 1, 2, 4. 1, 2, 4. So the length is 6. Okay? So this term represents the length of the shortest path of two edges between 1 and 4. Okay? And more generally, this matrix represents the length of the shortest path of two edges between any pair of vertices of the graph. Okay? And this is true for the second power, but also for the power k. Power k gives you the length of the shortest path consisting of k edges between any two pairs of vertices of a graph. This gives you a lot of information about the distance between two vertices in a graph. And this is why this distance product is widely used in graph theoretical algorithms. In particular, for graph theoretical problems known as the shortest path problems, which is a very widely studied problem, almost all the algorithms use one variation of this distance product. Okay, yeah. So it's very important. And so the max-min product is essentially the same. So the definition is a little bit different. You have max and min. But the interpretation is essentially the same. So you consider a graph here. And similarly, we associate the adjacency matrix, but instead of assigning infinity when there is no edge, you associate 0. Okay? And so A squared will be this matrix. Okay? For example, if you look at this entry, you can compute it explicitly here. And so it consists of 4 terms. And each term represents what we call the bottleneck of a path. So for example, here it's the bottleneck of the path from 1 to 4, which is defined as the weight of the smallest edge on the path. So here is the weight of the smallest edge in the path here, which is 1. Okay? And this is the amount of flow that you can send through this path. You can route through this path. So this term represents the maximal flow that you can send from 1 to 4 by a path of 2 edges. Okay? And this thing represents the amount of flow that you can, maximal amount of flow that you can send between any 2 pairs of the graph with a path of length 2. So this problem, computing the amount of flow that you can send between any 2 pairs using only 1 path, is called the all pairs bottleneck path. It's a very important problem in graph algorithms. So, and the point is that if you have an algorithm for this, computing the product over the max-min semirings, then you can use it to obtain fast algorithm for this problem. Okay? It's a very important problem. And the best known classical algorithm for these 2 problems is this complexity. Okay? So here complexity exponent 2.6864, and here it's the same, but if you consider the setting where you're interested only in the number of digit of precision. So for example, if S is constant, you want only a constant number of precision, a constant number of digit of precision, the complexity is the same n to the 2.6864. Okay? And the point is that the complexity is much worse than n to the omega, because we are working on semirings. So you don't have a subtraction. So you cannot use all the algebraic algorithms. So you don't know how to do it in n omega. So the complexity is much worse. But for both, there is a straightforward n to the 2.5 quantum algorithm. A very simple algorithm. Okay? And the algorithm is almost trivial. So for each pair ij, so for each entry of the output matrix, you simply compute it using an algorithm well known as a quantum minimum finding algorithm in order to compute this expression. So we know how to compute the minimum of n number in square root n times. And here we have precisely n, small n number. So you can compute this in square root n times. So you obtain this complexity. So we obtain something better than the best known classical algorithm. And what we have done, we have shown that we can do even better than this. Okay? So here we can further reduce the complexity to 2.4746. And here you can first obtain sublinear dependency in the exponent in S, and then you can also decrease this and obtain something smaller than 2.5 for the second part. And I will, in one slide, describe the second part. So the result, the complexity actually is this. So n to the 2 omega over 5, which gives you this bound using the best known on omega. And the idea is to look back at the classical algorithm for the problem. The classical algorithm has this complexity, as I said, 2.6864. But this algorithm works in 2 steps. First, it uses several matrix multiplication over a field. And then it uses an exhaustive search. Okay? And the point is that we can use quantum computation to speed up the second part. So this gives you an improvement, a direct improvement. But the direct improvement gives you a very small improvement. Nothing better than 2.5 in the exponent. So in order to break the 2.5 barrier here, we need to significantly modify the original algorithm, and this requires a lot of work. The main technique is simple, quantum search, but we need to be very careful, especially about the data structure we consider. Okay? And as an application, we obtain also an improvement for the graph theoretic problem I mentioned, the all pairs bottleneck problem. We obtain this complexity. And classically, the complexity is this. We obtain a gap here. So as a conclusion, the most fundamental open problem, these 2 ones, so for square matrix multiplication of a ring or for Boolean matrix, we still don't know if we can obtain better complexity in the quantum setting. But the main message I would like to convey today is that in several settings, you can still obtain faster quantum algorithm, and in particular for sparse Boolean matrix multiplication, for sparse inputs or sparse output, and also for matrix multiplication over several widely used semirings, such as the product, distance product, and so on. Okay, thank you.
Thanks, Francois. That was a really interesting talk. I have about 1 million questions, but there's one that's particularly bugging me. In the discussion of the Boolean matrix multiplications, you depended very heavily on an OR operation,
Yes.
which we know is difficult in a quantum context. So how do you deal with the consumption of resources necessary to do a logical OR?
Difficult in the quantum context, what do you mean? You mean in theory or in practice and implementation? I mean, it's essentially a Grover algorithm, computing the OR of many things. So it's really some task for which quantum computers are very good.
Yes, but so doing XOR is trivial, right? You use a C0 for that, right?
Yeah.
So how do you intend to actually implement the OR operation in your algorithm?
So
are you going to use a large set of ancilla states then, and a set of gates to do this?
So for the computation of the OR, we are using exactly the same algorithm as a Grover algorithm. Okay. So you take any implementation of a Grover search, and you can plug in into the circuits that you want to design in order to solve this problem. So Grover algorithm detect if there is one solution in a string of n elements. So Grover's algorithm compute the OR of n bits. This is exactly what we are doing. So for this task, we can use the same circuit.
Okay, I think I see.
I'm sorry, but I think that's a swap that is used in the Grovers.
Sorry?
I mean, it's not the OR in the classical sense. It's something like the swap algorithm.
The swap algorithm.
You use the swap during the algorithm, but the result of it is a certain element present or not. Is what you're accounting for the OR, right?
Yeah. So the thing that the algorithm is implementing is the OR, but inside this, indeed, it's used some swap operation, other kind of operation, but it's all ultimately simulating the OR operation. So fundamentally, it's an OR operation which is implemented.
Can you maybe explain a bit more how the input and how the input is given and the output?
Yes, so it's a very delicate question, actually. So in this talk, all the bounds I've given, almost all the bounds I've given are larger than n squared. Okay, there is only one exception for for output sensitive Boolean matrix multiplication. But for all the other things, so for example, so for all the other examples, the bound is larger than n squared. So for n squared, you can simply suppose that the input are given as an array, so matrix, explicitly. So you can read out everything and store them in memory, and then you can do whatever you want with them. Okay.
Some of the algorithm, you're saying that classical cannot do better because you have to read the whole input, right? So
Indeed, yeah. So you are talking explicitly on Boolean matrix multiplication, yes. So in this case, we suppose that the inputs are given as a quantum oracle, so quantum random access memory. So what you can do, you have an oracle and you can ask what is the entry in the ith rows and jth column. So you can ask this kind of queries and in superposition. So it's a model we are using for these kinds of applications.
How about computation of determinant and permanent?
Yes. Yes, about, yeah. more precise?
Computation of determinant
Yes.
and permanent of the matrix.
Yeah, so yeah, for determinant, yes, at least theoretically, it's the same complexity of matrix multiplication. So in the quantum setting, you can do the same. But for permanent, of course, the complexity is much more different. It's sharp P, and it's really something that we don't know any efficient quantum algorithm, and we don't even hope to obtain any efficient quantum algorithms to compute the permanent of a matrix. So they are really very different things. And determinant is connected to matrix multiplication. Permanent, it's not directly connected to matrix multiplication.
So in particular for the determinant, you cannot do any better quantumly than classically because it's the same as multiplication. Right?
Yes, exactly. Yeah, yeah. At least we don't. Yeah, yeah. We don't
So,
know what to do.
Let me try my luck at asking it for another problem than multiplication, but which is directly related.
Yeah.
In this case, transitive closure.
Yes.
Do you have examples where you can do better transitive closures quantumly, depending on which ring we're using?
I don't know any example in the quantum setting. I mean, the first thing that you can try to do is if you have a sparse graph, you can use all these things. But the problem is that if you use sparse graph and you're taking the power of the adjacency matrix, it won't be sparse anymore. So we are not able to use the improvement we obtain for sparse matrix multiplication. So I don't know any example where you can obtain the speed up for this computation of the transitive closure of a graph. Yeah, but this would be a very nice research direction. Maybe there exists some very specific class of graphs for which you can do this.
Any further questions?
So you said that we can find applications in case of shortest path algorithm in graphs.
Yes.
So will this help in any modification of the general algorithm that we have, like Dijkstra's algorithm or Kruskal's algorithm? Would it speed up?
Yes, so with this approach, you obtain some speed up with respect for many problems. So as you mentioned, for computing the shortest path and even other graph theoretic problems that I would like to stress, maybe I didn't stress it as much as I should have been, is that the results I mentioned are theoretical in the sense that we are using omega, the exponent of matrix multiplication. So we obtain very good asymptotic bounds. But in practice, there is a very huge constant hidden in the big O notation, so it's not some algorithm that you can use in practice. And in practice, it will be much faster if you use the algorithm you mentioned, Dijkstra algorithm and all these other things. So they are not really competing together. They are studying slightly different things. Yeah.
All right. I think we should stop here. Let's thank the speaker again.